Okay, we're going to look at a practice problem that just introduces the idea of an electric field. And this question reads, what is the magnitude and direction of the electric field produced by a charge Q equal to 2.3 microcoulombs at a distance of 5 meters away? Okay, so we have a charge Q where Q is equal to 2.3 microcoulombs. And we're interested in what is the electric field 5 meters from charged particle Q. So we're going to use our relationship for the electric field. We know that the electric field by charge Q is equal to K, capital Q, the magnitude of that charge, divided by the radius squared. So using that, we have 8.99 times 10 to the 9th times Q, which is 2.3 microcoulombs times 10 to the minus 6th, all over 5 squared. So our electric field has magnitude of 8.7 times 10 to the 2, so 870 newtons per coulomb. Okay, what's the direction of that electric field at that point 5 meters away? And let's say it's 5 meters on the horizontal. Well, since I have a positive charge Q, I know that the electric field points outward from that charge. And so at this point, 5 meters away, we would have a positive or rightward electric field directly to the right of positive charge Q. Okay, well, what if I changed it? What if I said, how would the electric field change if instead Q is equal to negative 2.3 microcoulombs? So it's not a positive charge, it's a negative charge. Well, the strength of the electric field isn't going to make a difference. It's going to be the same. We're still going to have 8.7 times 10 to the second newtons per coulomb, so 870 newtons per coulomb, even with a negative charge. But the direction of that field is going to be different. So if I'm looking at a point directly to the right of charge Q, my electric field will point to the left of magnitude 8.7 times 10 to the 2, or 870 newtons per coulomb. So the magnitude of that electric field is solely dependent on the strength of that charge and the distance away. We have to look at whether we're dealing with a positive or negative charge to determine the direction, as well as where that distance away we are. If I had my charge 5 meters to the left of Q, well, then the electric field 5 meters to the left would be pointing to the left. And the electric field of negative Q would be pointing to the right. So similar to what we did with the electric force, we have to pay attention to where specifically in space we are looking at that electric field. That's going to be particularly important when we have multiple charges and those electric fields are adding through superposition. And we have to pay attention to the the horizontal and the vertical components. So for a single point charge, it's pretty straightforward. There's another video that looks at 2 charges and how is the electric field affected by both of them together. Good job.